Hello and welcome. The higher heating value of biomass feedstocks is a crucial parameter for their energetic use, and it strongly affects the choice of suitable input materials. Usually, the calorific value is measured using an adiabatic oxygen bomb calorimeter. This method is highly accurate, but it's also expensive and time-consuming. Because of this, researchers have increasingly turned to regression methods and artificial intelligence techniques to predict the calorific value based on the chemical properties of biomass. In this video, we train an artificial neural network to predict the higher heating value of lignocellulosic biomass, using data from both ultimate and proximate analyses. Artificial neural networks can learn complex, nonlinear relationships between input and output data, even in large and intricate datasets. They mimic how biological nerve cells process information by using interconnected artificial neurons, also known as perceptrons. Their design is inspired by neuroscience and the way the human brain functions. However, it's important to note that ANN predictions are purely numerical. They don't provide direct physical interpretations, which is why they're commonly referred to as black box models. One widely used type of ANN is the feed-forward neural network, or FFNN. In an FFNN, information moves in just one direction, from the input layer, through one or more hidden layers, and finally to the output layer. There are no feedback loops or cycles, making this architecture especially well-suited for many problems in chemical engineering. Now, let's look at how a single neuron in an FFNN works. Each neuron receives input values, let's call them x sub I, from the previous layer. These inputs are multiplied by corresponding weight parameters, w sub g, then summed together. A bias term, b sub j, is added to this sum. The result is passed through an activation function, denoted as h, to produce the neuron's final output. Mathematically, the output of the jth neuron can be written as output sub j equals h of the sum, from I equals 1 to n, of w sub g times x sub I, plus b sub j. At the start of training, the weights and biases are initialized randomly. This randomness helps break symmetry and ensures that neurons learn different features during training. As the network trains, these parameters are continuously updated using an optimization algorithm to reduce the difference between the predicted output and the true target values. Finally, the choice of activation function, h, is critical. If a linear function is used, the network can only model linear relationships. But by using nonlinear activation functions, the network gains the powerful ability to capture complex, nonlinear patterns. This is one of the key strengths of neural networks. There are various types of feed-forward neural networks. In this video, the multi-layer perceptron is employed. A multi-layer perceptron consists of an input layer, one or more hidden layers, and an output layer, with all neurons between adjacent layers being fully connected. The input layer comprises 8 neurons, corresponding to the features: carbon, hydrogen, nitrogen, sulfur, oxygen, volatile matter, fixed carbon, and ash weight fractions. The output layer contains a single neuron that predicts the target variable, higher heating value. To evaluate architectural sensitivity, the hidden layer structure is systematically varied across 3 configurations. One with 128, 64, and 32 neurons, another with 64, 32, and 16, and a third with 32, 16, and 8 neurons. This allows for a comparison of performance across networks with differing capacities. To avoid overfitting and enhance the model's generalization capability, the dataset is randomly split into 3 subsets: training, test, and validation sets. 80% of the data are used for training, and the remaining 20% are reserved for testing. Within the training set, 10% of the data are held out as a validation set during the model training phase. Training is performed in mini-batches, with batch sizes of 32, 16, and 8 being explored to find the optimal trade-off between computational efficiency and stable convergence. The ADAM optimizer, short for adaptive moment estimation, is used as the training algorithm. It automatically adjusts the network weights based on the output of the loss function during training to accelerate convergence. Activation functions introduce nonlinearity into the model, enabling it to learn complex patterns. In this video, 3 activation functions are tested. ReLU, short for rectified linear unit, sigmoid, also known as the logistic function, and tan, or hyperbolic tangent, to assess the impact of nonlinearity. The ReLU function is defined as f of x equals the maximum of 0 and x. This function supports efficient learning by passing positive inputs unchanged while setting negative inputs to 0, thereby improving computational efficiency and helping to mitigate the vanishing gradient problem. The sigmoid function maps any real-valued input to a value between 0 and 1, following an S-shaped curve. It is given by f of x equals 1 divided by the quantity 1 plus e to the power of negative x. The tan function outputs values in the range from -1 to +1 and is 0-centered. It is expressed as f of x equals e to the x minus e to the negative x, all divided by e to the x plus e to the negative x. While tan provides stronger gradients than sigmoid and can improve convergence in some cases, it still suffers from the vanishing gradient problem when inputs become very large in magnitude, either positive or negative. As a regularization technique, L2 regularization is applied to prevent overfitting and improve generalization. L2 regularization discourages the model from becoming too complex by penalizing large weights. It does this by adding a penalty term to the loss function that grows as the weights get larger. The strength of this penalty is controlled by a parameter called alpha. If alpha equals 0, there is no regularization. Only the original loss is used. If alpha is large, the model strongly penalizes large weights, leading to a simpler, more generalized model, but possibly underfitting if alpha is too high. In this video, different alpha values, 0.0001, 0.001, and 0.01, are tested to find the optimal penalty strength. Early stopping is used to terminate training if the validation score, defined as the coefficient of determination, or R-squared, fails to improve for 10 consecutive epochs. The mean squared error, or MSE, serves as the loss function and is used to evaluate model performance. While the loss function is optimized during training, the validation metric, R-squared, is used to trigger early stopping. R-squared and MSE are calculated using the equations. R-squared equals 1 minus the sum from I equals 1 to n of the squared difference between y sub I and y hat sub I, all divided by the sum from I equals 1 to n of the squared difference between y sub I and y bar. MSE equals 1 over n, multiplied by the sum from I equals 1 to n of the squared difference between y sub I and y hat sub I. Here, n is the number of data points, y sub I represents the actual observed value, y hat sub I is the model's predicted value, and y bar is the mean of the actual values. R-squared measures the proportion of variance in the target variable that is explained by the model. In contrast, MSE quantifies the average squared deviation between the actual and predicted values. An R-squared value close to 1 indicates high predictive accuracy. Generally, R-squared values above 0.7 are considered acceptable, and values above 0.9 are regarded as excellent. For MSE, an optimal model produces a value close to 0. However, because MSE squares the errors, it is sensitive to outliers. Large prediction errors are penalized more heavily. Both R-squared and MSE are also used to quantitatively evaluate the predictive performance of the ANN model. The ANN model is implemented in Python using the following libraries: pandas for data loading, manipulation, and analysis, NumPy for numerical computations, scikit-learn for implementing the MLP regressor, constructing pre-processing pipelines, performing hyperparameter optimization via grid search CV, and computing statistical evaluation metrics, matplotlib, pyplot for creating fundamental plots and figures, and seaborn for advanced visualizations. To enable efficient training and good convergence of the ANN model, standardization of the input data is essential. The widely varying ranges of the parameter values highlight the critical need for feature scaling prior to training. The standard scalar function from the scikit-learn library is used for this standardization. It transforms each feature to have a mean of 0 and a standard deviation of 1. This process consists of 2 steps. First, centering, subtracting the mean of each feature so that the resulting mean is 0. Second, scaling, dividing by the standard deviation of the feature so that the resulting variance is 1. A comprehensive literature review on the proximate and elemental analyses of lignocellulosic biomass was conducted to compile a diverse and representative dataset for modeling. Particular emphasis was placed on including a wide variety of biomass types during sample selection. Using biomass with similar properties would increase the likelihood of such samples being disproportionately represented in the training dataset, potentially leading to biased model predictions. Proximate and elemental analyses were compiled for 220 agricultural residues, 52 energy crops, 73 hardwoods, and 42 softwoods. The proximate analysis is reported on 2 reference bases, as received and dry. The ultimate analysis is reported on 3 bases, as received, dry and ash-free. The as received condition means the biomass sample underwent no pre-treatment prior to analysis. On this basis, the proximate analysis, comprising volatile matter, fixed carbon, ash, and moisture, sums to 100%. Similarly, the ultimate analysis, comprising carbon, hydrogen, nitrogen, sulfur, oxygen, ash, and moisture, also sums to 100%. When moisture is completely removed, the composition is expressed on a dry basis. On this dry basis, in proximate components, volatile matter, fixed carbon, and ash sum to 100%. Likewise, the ultimate components, carbon, hydrogen, nitrogen, sulfur, oxygen, and ash sum to 100%. The relationship between the as received and dry basis is defined by the conversion formula. The mass percentage of any component on a dry basis equals 100 divided by the quantity, 100 minus the as received moisture content, multiplied by the component's as received mass percentage. Here, the component I can be carbon, hydrogen, nitrogen, sulfur, oxygen, volatile matter, fixed carbon, or ash. When both moisture and ash are excluded, referred to as the dry and ash-free basis, the ultimate analysis includes only the combustible elements, carbon, hydrogen, nitrogen, sulfur, and oxygen, which together sum to 100%. Note that DAF stands for dry and ash-free. Conversions between bases for the ultimate analysis follow 2 key equations. First, to convert from as received to dry and ash-free, the dry and ash-free mass percentage equals 100 divided by 100 minus as received moisture minus as received ash, multiplied by the as received mass percentage. Second, to convert directly from dry and ash-free, the dry and ash-free mass percentage equals 100 divided by 100 minus ash content on a dry basis, multiplied by the dry basis mass percentage. To ensure a consistent basis for training the artificial neural network model, all data not originally reported on a dry basis were converted to a dry basis. Specifically, a data reported on an as-received basis were converted to dry using the formula from the previous slide. A data reported on a dry and ash-free basis were converted back to dry by rearranging the second formula. The linear correlation between any 2 variables was quantified using the Pearson correlation coefficient, commonly abbreviated as PCC. The PCC is calculated by taking the sum of the products of the deviations of each variable from their respective means, and then dividing that by the product of the square roots of the sums of square deviations for each variable. The Pearson correlation coefficient measures the strength of the linear relationship between 2 variables. Its value ranges from -1 to +1. A value of +1 indicates a perfect positive linear correlation, 0 indicates no linear correlation, and -1 indicates a perfect negative linear correlation. Here we see the dataset in Excel. The first column, biomass sample, serves as an identifier for the specific type of biomass. The adjacent column, biomass category, classifies each sample into one of 4 groups: agricultural residues, energy crops, hardwood, or softwood. The core predictive inputs are organized into 2 major analytical sections: ultimate analysis and proximate analysis. In the ultimate analysis section, the elemental composition, carbon, hydrogen, nitrogen, sulfur, and oxygen, is reported on an as-received, dry, or dry and ash-free basis. In the proximate analysis section, the components, moisture, volatile matter, fixed carbon, and ash, are specified on either an as-received or dry basis. The target variable, higher heating value, is clearly labeled with its unit and stated on a dry basis. The source column provides the academic reference for each data entry. Finally, the inputs columns show all relevant values converted to a dry basis for consistency in modeling. Now we're starting to write the Python code. I'm using Jupyter as the platform. I prepared the data as a CSV file, so we can proceed with the Python code and load the data. As previously mentioned, the dataset consists of 387 entries and 9 features. The first 8 columns represent the compositions of carbon, hydrogen, nitrogen, sulfur, oxygen, fixed carbon, volatile matter, and ash. The 9th column, higher heating value, is the target variable of this dataset. The data info section confirms that there are no missing values in any of the 387 entries across all 9 columns. The Pearson correlation matrix heat map reveals key relationships among the ultimate and proximate analysis components and the higher heating value. Carbon shows a very strong positive correlation with higher heating value, indicating that biomass richer in carbon generally yields more energy. Hydrogen also positively correlates with higher heating value, though less strongly. In contrast, ash exhibits strong negative correlations with both carbon and higher heating value, underscoring that higher ash content reduces both carbon concentration and energy output. Fixed carbon and volatile matter are strongly inversely related, reflecting their complementary roles in biomass composition. Other elements show weak or negligible correlations with higher heating value and with each other, suggesting they play a minor role in determining the heating value in this dataset. Overall, the analysis highlights carbon, hydrogen, ash, and the balance between fixed carbon and volatile matter as the dominant factors influencing fuel quality and energy potential. The parameter random state equals 42 is very important. It ensures that the data split is reproducible. By using this specific seed for the random number generator, anyone who runs this code will get the exact same division of data. This reproducibility is essential for debugging the model and for reliably comparing results between different runs. In the presentation, we did not see max_error and learning rate. To keep training efficient and avoid unnecessary computation, the process is capped at a maximum of 2,000 iterations. The learning rate is set to adaptive. So if training progress stalls, the rate automatically adjusts, helping the model converge toward a better solution. The goal of Grid Search CV code is to leverage the systematic hyperparameter combination machinery of Grid Search CV on the training data alone. This is achieved by a specific configuration that uses the entire training set for both training and validation via the CV parameter, effectively bypassing cross-validation, to efficiently fit and score all models on X-train and Y-train. After this initial fitting phase, the code performs a crucial manual evaluation to assess the true generalizability of each tuned model. It creates an empty list, called test_scores, to store performance on the unseen test set. The code then iterates through every parameter combination tested by the grid search. For each one, it manually configures the pipeline with those parameters, refits it on the entire training data, and then calculates its performance score on the held-out test set, X-test and Y-test. This step is vital because the scores from the grid search itself are based on the training data and are therefore overly optimistic. The test scores provide an unbiased estimate of performance on new data. Finally, the code presents a detailed report. It prints a summary for every parameter combination, listing the parameters, the training score, R², the test score, R², and their difference. This score difference is a key indicator of overfitting. A large positive value suggests the model has memorized the training data and does not generalize well. The report concludes by highlighting the best parameter set according to the grid search, based on the training score, and its corresponding performance on the test set, providing a final assessment of the best model's expected real-world performance. Here we see the results of 81 combinations. We proceed with the suggested best combination. With the calculator, we reach the end of the video. If you're interested in the data, code, presentation, and a description of the method in a Word document, please see the video description.